In this lesson, we're going to talk about the isotopes and radioisotopes.
In the early 20th century, the discovery of isotopes revolutionized the field of
Chemistry and physics, and the term isotope was first used in 1913 by Frederick Soddy, a British radiochemist who realized that certain elements had atoms with different numbers of neutrons. The term isotopes means the same element with the same proton and electron number, but different number of neutrons, resulting in different atomic masses. For example, carbon-12 and carbon-14 are both isotopes of carbon, but carbon-12 has 6 neutrons, whereas carbon-14 has 8 neutrons. And isotopes can be stable or unstable, depending on the balance between the forces that hold the nucleus together and those that try to break it apart. Different elements have different numbers of isotopes, and these specific isotopes exist in different relative abundances, or the percentages they exist in the element. For example, natural magnesium is a mixture of three isotopes, which are magnesium-24, magnesium-25, and magnesium-26. On average, a sample of a natural magnesium consists of 78.7% of magnesium-24, 10.1% of magnesium-25, and 11.2% of magnesium-26, as shown in this diagram here.
And you might be wondering, how do scientists get the percentages?
Well, they use a mass spectrometer to identify isotopes and their respective abundances. And you don't have to know how it works, but I'll still briefly go through it. So first of all, a mass spectrometer vaporizes a dissolved sample by using heat, and then ionizes the sample. Subsequently, the sample will travel in a chromatography column, so basically this tube over here, and the ions can be separated by mass using a magnetic field. And finally, a detector will detect their abundances, and a computer will determine the isotopic composition by comparing the value with a database. And mass spectrometers are very useful in chemistry. They can perform a variety of analyses, such as identifying proteins, detecting pollutants in the atmosphere, and even running a drug test in sports. Radioactive substances spontaneously break apart. This integration is known as radioactive decay. And as some isotopes decay, they emit nuclear radiation in the form of tiny particles or energy. In question red, what does spontaneous mean? You have 1 minute to think about that. And if you look it up in the dictionary, spontaneous means happening or done in a natural, often sudden way, without any planning or without being forced. In this case, the radioactive substances break apart without being forced. As we have seen from the previous slide, some elements have more than one isotope, and scientists noticed that some isotopes are stable while others break apart easily. And the difference in stability is due to the composition of the nuclei. The unstable isotopes undergo radioactive decay, which is a process by which they lose energy and transform into other elements. And there are several types of radioactive decay, such as alpha decay, beta decay, and gamma decay, and they will change the atomic number and the atomic mass of the resulting element. And I'm going to illustrate each of them in the next slide.
Now, let's learn about the alpha particle, beta particle, and gamma ray.
An alpha particle is a positively charged particle with the same structure as the nucleus of a helium atom. So it consists of 2 protons and 2 neutrons as shown here. A beta particle is a negatively charged particle which is identical to an electron, as shown here. And gamma ray is a form of high energy electromagnetic radiation, so it's a form of energy, therefore it has no mass and no charge. And alpha particles are the most reactive because they're big and they have a strong positive charge. And beta particles are smaller than alpha particle, therefore it is less reactive. And gamma rays are the least reactive but most penetrating. So here is a comparison between them in terms of their reactivity and their penetration level.
We have a name for the unstable isotopes that decay to produce nuclear radiation, and we call them
radioisotopes. For example, all of the isotopes of uranium are radioisotopes because there are no stable uranium isotopes at all. And actually, one of the components in a nuclear bomb is uranium-235. And here's a picture of uranium if you want to take a look.
And how do we determine the atomic mass for an element?
So look at the periodic table and find the atomic mass for chlorine. And as you may notice, it is not a whole number. The atomic mass for chlorine is approximately 35.453 AMU, or atomic mass unit. And what does this number represent? And why is it not a whole number? And how do scientists find the value? And now we're going to figure this out together. When we calculate the atomic mass, we should consider both the mass and the abundance of each of the different isotopes of an element. And the atomic mass equals the percentages of abundance of isotope 1 multiplied by mass of isotope 1 plus the percentages of abundance of isotope 2 multiplied by the mass of isotope 2, and keep going. And this calculation gives the atomic mass. And that's how isotopes and atomic mass are connected. And in this case, we just substitute a number and find that the atomic mass of chlorine is 35.4846, which is a bit different than this value, and that is because we use data from different databases. And here's how Nelson textbook solves the atomic mass for germanium. And yeah, it is the same as what I did. But keep in mind that you don't need to round the answer at the end. You just keep it at 72.71 for accuracy. And here's a summary for this section. You guys can pause the video and copy them down to your note. And here I've got some questions for you. So just calculate the atomic mass for each of the following elements. And that's about it. Thank you for watching, and I'll see you in the next episode.